Hi there, I'm JD Zamfirescu-Pereira, and I'm happy to present our work, Trucks Don't Mean Trump, Diagnosing Human Error in Image Analysis, in collaboration with Chen, Emily Wen, Allison, Koenecke, Nikhil, Garg, and Emma Pierson. People often have to analyze images in high-stakes settings. Doctors evaluate scans, content moderators assess photos and videos, and pilots respond to fast-changing visual data. In this work, we develop a machine learning approach to analyze the ways in which humans err in doing so. In this talk, I'll start by discussing the unique dataset we use to evaluate and explore these methods. Then I'll describe our method and some of the results it yields. Then some alternatives we considered but ultimately dismissed. And finally, I'll end with some applications we hope to see in the future. Let's start with data. For this work, we relied on a unique dataset provided to us by the awesome New York Times interactive team. 16 million human predictions of whether each of 10,000 neighborhoods voted for Trump or Biden in the 2020 election, based only on a Google Street View image presented to readers as part of an interactive experience. This data is cool because it has more than 1,000 human judgments on each image, plenty to compute a meaningful aggregate judgment, and a ground truth defined independent of that human judgment, each precinct's relative vote share. An independent ground truth is unusual. For example, in radiology, ground truth in datasets is commonly an aggregate of expert opinion on that image itself, not an assessment independent of human judgment. That independence we think is key here, because otherwise studying human error would be circular. Plotting the Trump-Biden vote margin, x-axis here, against aggregate human judgment, the y-axis, we see that while correlated with true election outcomes, humans are far from omniscient and frequently disagree on each image. Nevertheless, these deviations from vote share are not enough to conclude that humans are making avoidable mistakes. It could be that the images are uninformative about election outcomes, and so the errors are unavoidable ones that would be made even by a Bayes optimal decision maker, that is, one that always chooses the most likely outcome given all the available information. How can we understand whether the errors humans make are avoidable or unavoidable? Consider a Bayes optimal decision maker making binary decisions about these images, Biden or Trump. Given a probability that a neighborhood votes for Trump, yi equals 1 here, given an image of that neighborhood, that's xi here, that decision maker should predict if the probability is greater than 0.5, then the neighborhood voted for Trump. In this work here, formally, we aim to quantify to what extent do human decision makers, individually and in aggregate, deviate from Bayes optimality, and then try to understand and identify which image features lead to these deviations. These errors are potentially avoidable, but identifying them is tricky for a few reasons. We don't have access to this probability, nor human estimates of the probability, only individual binary decisions, and then defining which image features are salient is also hard in general. We'll tackle each of these issues in turn. First, to estimate the probability that a neighborhood voted Trump based only on the images of that neighborhood, we trained a neural machine learning estimator using tens of thousands of Street View images and the known vote share of those neighborhoods' precincts. This estimator performs reasonably well, better overall than the human aggregate judgment, suggesting that there is indeed signal present in images that humans miss. Second, using the New York Times dataset, we fit a simple logistic regression using our trained neural model and the aggregate human judgment as features. And we use this regression model as an estimate of a Bayes optimal model, an overall estimate of the probability that a neighborhood voted Trump based on the image data and features derivable from it. The regression over the neural model and human judgment lets us verify that our neural model adds significant relevant signal beyond human judgment. Otherwise, its coefficient in the logistic regression would be 0, and it isn't. Conversely, the human model's coefficient is also not 0, suggesting there is signal that humans pick up on, but the neural model misses. Combining the two yields a better approximation of the Bayes optimal decision. So how do aggregate human judgments differ from the decision implied by our Bayes optimal model? If humans were acting Bayes optimally, we should expect to see a threshold function at probability 0.5. But we don't see this at all. Instead, what we see suggests that humans are making avoidable errors, decisions which deviate from those of the estimated Bayes optimal decision maker that has access to the same image data the humans do. As a preliminary assessment of human error, let's manually inspect images where aggregate human judgment deviates substantially from our estimator. For example, the images in the top left corner of this figure. Our estimator predicts that these images are quite likely, with about 80% plus probability, of neighborhoods that voted for Biden, while humans in aggregate are more than 60% confident that they are not images that voted for Biden. By looking at the known vote share for each of these neighborhoods, we see that over 80% indeed did vote for Biden, indicating that humans are making avoidable errors on these images. As you'll see, these images also disproportionately have pickup trucks, suggesting that people think trucks indicate Trump more than they really do. The relationship between trucks and Trump is corroborated by interviews the New York Times conducted with a sample of their respondents to the interactive piece. Starting with a good ML-based estimator, one that takes only image data as input and estimates a probability that a precinct votes a certain way, we can then approximate, or at least place an upper bound on, the amount of noise present in these images. That is, the amount of unavoidable error that is due to the intrinsic unpredictability of the outcome from the image of the features itself. Then, with noise set aside, our model also allows us to estimate how much human error is then caused by bias, that is, suboptimality in the aggregate human decision, in the wisdom of crowds. Bias here is the amount of accuracy loss in the aggregate human decision that isn't caused by noise. Our upper bound on noise means we have a lower bound on bias here, implying that bias is at least as large as we found, and possibly larger. Finally, variance captures suboptimality due to random variation across individual humans. This decomposition of human error into bias, variance, and noise terms, enabled by our estimator, is analogous to the classic decomposition for machine learning classifiers. In our data, accuracy loss due to bias is smaller than that due to variance and noise, suggesting that humans in aggregate are actually pretty good at this task thanks to the wisdom of crowds, even though individual humans are erratic and there is a lot of unavoidable error. This decomposition is actionable. If, for example, doctors mainly lose accuracy due to bias, we might retrain them. If they are accurate in aggregate but individually high variance, we may need second opinions. And if the images are noisy, we may need an alternate diagnostic modality. Instead of an X-ray with high noise, for example, high unavoidable error, maybe direct examination of a biological sample is better. Our earlier manual inspection of images with a mismatch between aggregated human prediction and our estimator showed that these deviations can provide insights about image features which lead to human bias. But can we systematically predict from an image where human judgment will deviate from the Bayes optimal estimator? If there are image features that produce systematic deviations, it suggests that humans are influenced by these features beyond what our model would justify. To find these systematic deviations, we train a second model to predict how much aggregate human judgment deviates from what we would expect given our estimator. First, we flexibly capture how aggregate human judgment tends to vary with the model estimated probability. That's the orange line here showing the fit. Then, we calculate the residual, the difference between the aggregated human judgment and this fit line for each neighborhood. If there are image features that predict this residual, this suggests that the image features lead to inconsistent human judgments about images with the same estimated probability. And finally, we train another neural network to predict this residual and run an occlusion mapping technique to identify image patches that impact the residual. These image patches show image features that lead humans to predict Trump on the left side, or Biden on the right side, more often than would be justified by the image features alone. In other words, humans overweight these kinds of image features in making their predictions. Patches of sky and other markers of low density, like road edges without curbs, on the left suggest that human respondents are more influenced towards Trump by features suggesting low population density than the estimated probability would explain. Conversely, on the right, we see cars, street lights and street signs, and sidewalk curbs, suggesting that humans overweight these markers of higher population density as well. Using publicly available demographic data, we can verify analytically whether the human aggregate judgment overestimates Trump in low population density neighborhoods and overestimates Biden in high population density neighborhoods, and we find that they do. Humans in aggregate judge neighborhoods that have above median population density as more likely to vote for Biden across nearly the full spectrum of estimated probabilities. Of course, this finding is only interesting to image analysis through the assumption that image features in the neighborhood images correlate with this underlying demographic data. That seems plausible. In developing the method we described here, we also considered and ultimately dismissed a few other approaches. I'll talk about two now. This first approach we call the two models approach. In this approach, in addition to training a model to estimate ground truth as before, you also train a model to estimate human judgment. Accuracy on this model can be pretty high, that is, has a low noise component, unlike the ground truth model, so we can feel pretty confident that humans are only judging based on the data in the image. In our testing, we routinely found binary accuracies above 90%. Then, you compare salient features of both models. Unfortunately, as you see here, systematic comparison is hard. Even identifying salient features for a single model is hard and an active area of research. It's also unclear how these features reflect bias. So we show image patches here identified by the same occlusion mapping technique we used earlier that most influence the human judgment, the left column, and ground truth, the right column, these are both models, remember, to predict Trump in the top row or Biden in the bottom row. You can still see clear correlates with density, but it's not clear what features humans are weighting in error. The second approach trains a model to directly predict the difference between the average human judgment and the ground truth vote share. Though this approach is intellectually appealing, requires training only a single model, and is simpler than both the two-model approach just described and the main approach described by the work, it does have a fatal conceptual flaw. It doesn't distinguish between useful features and overweighted features, if those features correlate with but don't perfectly predict the outcome. For example, suppose the only informative feature is whether the image has a car in it, and that 70% of images with cars vote for Trump, while 20% of images without cars vote for Trump. Then, a Bayes-optimal human will always classify images with cars as voting for Trump, and images without cars as voting for Biden. The model will correctly learn that cars predict the difference, but then imply that humans are overweighting cars, even though in fact humans are using the presence of cars in a Bayes-optimal manner, and the error actually stems from the fact that the images are not sufficiently informative. Our approach solves this by not using ground truth directly, but instead using probabilities based on the image data itself, reducing the error caused by noise, and then adapting that output to scale those ground truth probabilities to the human probability range. We hope the methods we describe and explore here will be more broadly useful. You can follow our playbook on other image or non-image datasets with human or algorithmic judgments and an objectively defined ground truth, and those datasets are becoming increasingly available. Here are a few examples from the Nightingale Open Science Initiative, founded by faculty from UC Berkeley and University of Chicago. It's worth noting that our method is in principle applicable to black box algorithmic decision-making systems as well, not just human decision makers. This has been Trucks Don't Mean Trump, Diagnosing Human Error in Image Analysis. For even more details, see our paper. Thanks for listening.